Thank you so much, Scott. Hi, everyone. Today, I want to give you a small introduction to the reftable format, which is a new backend to store references in your Git repository. First, who am I? My name is Patrick Steinhardt. I'm a huge Linux fan since 2002. I have started contributing to various different open source projects in 2011, and I'm a Git and libgit2 contributor starting 2015. I've also joined the Git team at GitLab in 2020. But that's enough of myself. Let's get started with the actual topic. First, let's actually figure out what we're talking about today and give you a quick refresher of the actual topic. So let's start at the beginning and talk a little bit about the GData model. While some of this may be familiar to many of you, it's always helpful to revisit the core concepts as we move forward. All of your Git data in a repository is stored in objects. There are multiple different object types. First, you have your commits. Those store the history and how it evolves over time. They store commit messages, as well as metadata about the author. Each commit points to a tree. You can think of a tree like a directory. Just like a directory contains entries pointing to other directories and files, trees have entries pointing to other trees or blobs. And finally, the blobs themselves, which contain the actual data of your repository, like, for example, your code. As some of you may know, Git objects are actually content addressable. What this means is that the name of an object can be derived from hashing its contents. The result is a long hex string that you can use to address your object. Of course, nobody really wants to remember those long hex strings, and this is where references come into play. References assign readable names to objects and their hashes so that you don't have to remember those long strings. There are different kinds of references. Branches, for example, start with refs heads, tags start with refs tags, references of remotes start with refs remotes, and so on. There's also a special head reference. This reference typically does not point to an object ID directly, but to another reference. This is a so-called symbolic reference, and it typically indicates the currently checked out branch in your repository. When creating or updating references, they're by default stored in the so-called loose format. Every reference you have is stored in a separate file. The reference format is really quite straightforward and really easy to grasp. To demonstrate, let's create a simple repository with a commit and a branch. The first file we'll examine is head. As mentioned before, this file indicates what your currently checked out branch is. As you can see, it has a ref prefix, which indicates that this is a symbolic reference, where the target is refs heads main. So we know that the main branch is checked out in this repository. All the other references are stored in the refs directory hierarchy. As we can see, we've got two files in refs heads, namely feature and main. These are our branches, and as we can see, they have an object ID they're pointing to as their contents. Now, storing every single reference in a separate file works well when you only have a handful of references in your repository. But when you have hundreds or even thousands of references, it starts to become really inefficient. Every reference needs a separate inode, which typically means on many file systems that they restore a full disk sector of disk space. Listing all your references also becomes increasingly expensive, as you have to read many, many files to list all of them. Git regularly packs their references to counteract this. Instead of storing all your references in separate files, they get packed into a packed refs file. You can manually pack references by executing git pack refs --all. Git usually does this for you automatically as part of maintenance routine, which it runs after several commands, like, for example, git commit. As you can see before and after executing git pack refs --all, both of our loose references have vanished now. Instead, we now have a packed refs file, which is a simple sorted list of all the references in your repository that have currently been packed. So you now have a little bit of background of what we're talking about today and how Git stores references in the files backend. So the next question is, why does it actually need to change? There's a bunch of problems, where the first problem is that file systems are weird. Conceptually, they're rather simple, but the devil lies in the details as ever so often. Did you, for example, know that Windows reserves all kinds of file names and keeps you from creating them? This is legacy baggage stemming from the DOS era, and because of it, you cannot create the branch that is named com, prm, aux, null, com1 to 9, or also lpt 1 to 9. Also, file systems like FAT, NTFS, or HFS+, for example, are case insensitive by default. And again, what this means is that you cannot create two branches that only differ in casing. macOS also does kind of weird stuff to your branches, because they change the way your file names are encoded in the case they contain Unicode characters. So what Git wants to store on disk and what macOS actually ends up storing on disk might actually be different, which creates more problems. In the best case, you know that all of these restrictions apply. In the worst case, you have a colleague who simply doesn't like anybody who is using Windows, and this creates a branch that is named com1 to make your life as painful as possible. The second problem is that the design is inefficient. If you want to write 20 references, you have to create 20 separate files. This doesn't only take long when you consider performance, but for typical file system, this also means that each of those references requires 4 kilobytes of storage, and that adds up rather quickly. Packing references is expensive, but mandatory when a repository has many branches to retain good performance. You have to rewrite the complete packed REST file on every single repack, which is typically fine for repositories that only have a handful of branches. But Git users aren't always reasonable. One of the worst repositories that we host at GitLab has 20 million references, and that adds up to a packed REST file that is more than 2 gigabytes in size. Which actually brings me to the next point. Deleting references also requires us to rewrite the complete packed REST file, which means that every time somebody deletes a single reference in your repository, you have to potentially rewrite more than 2 gigabytes of data. And to add insult to injury, this repository typically deletes references every couple of seconds. The third problem is that concurrency is an afterthought. There are multiple issues with representing references as single files when you have multiple readers and writers in your repository doing stuff at the same point in time. One of the problems is that it is impossible to get a consistent view of all the references. To get that, you would have to open multiple references and multiple different files, and each of them could change at any point in time. So when somebody writes to the repository while you read references, you cannot tell whether you actually got a consistent state of the references or whether you got a mixed state of the old and the new states. Similarly, it is also impossible to atomically write more than one reference at the same point in time. Each reference you want to write is a separate file, and thus you cannot commit all of them at once. There's also no way to lock the whole reference database. While there could conceptually be a central log file, introducing that retroactively would likely break all kinds of use cases out there. So we've now heard several reasons why the current reference storage format is insufficient and why it has to change and have a major redesign. So when did that whole redesign take place? Well, as Scott mentioned, this has already been ongoing for a very long time. In fact, the whole effort to introduce the alternate backend to store references has started 11 years ago in 2013. The project once again discovered some kind of race condition with a packed REST file that could lead to data loss in your repository, and figured it might be actually time to design a better replacement for the reference backend. The first design for making the reference backend pluggable in the first place hit the mailing list in 2014. It wasn't yet clear how the new format should look like, but there were a bunch of restrictions. Databases like SQLite, for example, were considered, but ultimately not pursued because JGit, for example, couldn't use it. Several other databases were also discarded due to licensing concerns. So the next 2 years were spent on slowly refactoring the code base to make pluggable reference backends a thing in the first place. In 2017, we then finally had the first RFC for the reftable backend, as well as an initial implementation in JGit. The technical document for the format landed in 2020, the reftable library that allows reading and writing tables landed in 2022, and then finally the reftable backend that ties it all together landed in 2024. So apparently, this huge odyssey in this timeline is what you can expect when working on a huge change like this in the Git project. So we've now talked about the old backend and why it had to change. Let's finally get to the meat of the reftable backend. First, you can create a repository with a reftable backend by passing the --ref format equals reftable parameter to either git init or to git clone. That's basically all that you need to know, because the repository is expected to behave the exact same as before. But still, let's have a deeper look at the actual structure of the repository. Curiously enough, we still have the ref directory hierarchy, and we also have the head file in here, which were also present in the files backend. But we now also have a reftable directory with a single table and a tables.list file in there. First, let's have a look at our head file. As you can see, it still looks like a symbolic reference, but it points to refs heads.invalid, which is in fact not a valid reference name. This file really only exists as a compatibility shim, because Git does not consider a directory a repository unless it has a head file. The second step we have is refs heads. In contrast to a normal repository, this is not a directory, but it is a file that contains garbage. If Git clients try to read that with a file backend, they would actually be expected to fail, which is a safety mechanism to keep them from writing to that repository. The git config file also looks a little bit different. Most notably, it now got a ref storage extension at the end, where the value is reftable. This indicates to the Git client that this is a reftable-enabled repository. The first data structure that is specific to reftables is the tables.list file. This file tracks the currently active list of tables in this repository. So whenever you update a reference, Git will write a new reftable appended to this list. This mechanism is really, really important because it allows for atomic updates. You can get a consistent snapshot by reading the tables.list file and then loading all of the reference tables. And you can perform an atomic write of multiple references by first creating a new table, creating a temporary tables.list file and appending the new table to it, and then renaming the temporary tables.list file into place. The tables themselves are actually stored in binary format, but diving into all the intricate details would actually lead us too far down the rabbit hole of reftables for today. While the binary format is more complex than a text-based format, it allows us to store data more efficiently. Also, as reference names are not encoded by their file system path anymore, you can actually store your precious refs heads com1 branch even on Windows systems. If you squint really hard, you'll still be able to see a few things in this binary file and the hex stub of it. First, there's a reft prefix that indicates that this is a ref table. It marks the header of this file, encoding various kinds of metadata. There also seems to be something like a footer, which is also indicated by the second reft string, which again encodes some metadata about this file. You can also see that there's a head file, head reference in there, which seems to be a symbolic reference pointing to refs heads main. As I've mentioned already, Git will append a new table to your tables.list file whenever you update the reference. So when we create a new commit, you can see that our tables.list file now has two entries, the old table that we already had and a second one. Note how the second table we have added has a counter value of 2. This is called the update index, and it increases whenever you perform an update of references in this repository. We'll get back to this a little bit later, at which point I will also explain why this counter exists twice. But for now, let us inspect the new table with another hex dump. We can see some interesting things. We again got the reft header and also the footer. We've got our refs heads main reference. And the reference is also followed by the object ID of the newly written commit. Note that this object ID is not encoded in hex, but directly in binary, which is way more efficient. We now look at what it looks like when updating a single, we now know how it looks like when updating a single reference. But what happens when we update multiple references in a single transaction? We can do that by using git update ref --stdin, where we now create two branches, branch 1 and branch 2, which both point to the object ID of our head reference. And again, this only ends up creating a single new table that contains both of the updates, which is an atomic operation, and this solves another issue that we have with the files backend. Curiously, if we have a look at the table, we can only see the name of one of those two branches we have created. But the second one is in there as well. Here it is. Namely, the thing is that in reftables, we actually have a lot of common prefixes for every single reference, which is typically, for example, refs heads. Repeating that full prefix for every single reference would actually be a waste of precious disk space. So the reftable format uses so-called prefix compression, where each record can reuse bytes from the preceding record's name. So in this case, we only have to store the differing byte, namely the byte 2, and everything else will be reused from the presetting record. Of course, we cannot just keep on appending new tables whenever we write a reference, as that would quickly get out of hand if we had hundreds or even thousands of them. To prevent the list from growing out of hand and too long, we use autocompaction. Whenever we append a new entry to the list, we check whether some tables should be merged together. So let's create another branch. As you can see, this time around, we didn't append a new table. Instead, we end up with a single merged table. I've already mentioned the update indices before. And they were the same before. But now that we actually have a merged table, we can see that the first number refers to the first merged table, and the second number refers to the update index of the last merged table. The reftable backend uses geometric sequences as a heuristic to decide whether or not to merge tables. Each table must be at least twice as large as the next smaller one. If that geometric sequence is violated, we'll merge as many tables together as required to restore that property. You can see that property come into play quite nicely when you create a lot of branches, like in this case where we create 1,000 different branches. Another problem with the files backend was the high cost of deleting references, since it required rewriting the complete packed rest file. The reftable backend solves this by treating deletions like any other update. Instead of rewriting the tables, we actually only append a new table to the stack with a marker indicating the reference as deleted. So you now have a rough understanding of how the reftable backend operates. But how does it actually perform? We can have a look at a couple of benchmarks to answer this question. The first benchmark is creating refs sequentially, each in their own transaction. The y-axis represents the time in milliseconds, where lower is better, while the x-axis shows the number of references created. Unfortunately, we can see that the reftable backend is actually slower than the files backend. This isn't entirely surprising, though. It cannot get much cheaper than with the files backend, where you only have to create a single small file to update a reference. Compared to that, the reftable backend has to open the tables.list file, parse the tables, and then append the new one. What's even more important, though, we're comparing apples to oranges. The end result when writing 10,000 references with the files backend is 10,000 separate files, and scanning through them will be very expensive. On the other hand, the reftable backend is self-optimizing when you write. So after writing 10,000 references, we'll actually end up with 7 files in total. So if you think about it, it's actually quite amazing that the reftable backend is only slower by such a small margin. But let's get to more exciting use cases. Writing many references atomically in a single transaction. This time, the x-axis shows how many references we create in that transaction. And indeed, this is where the reftable backend really starts to outperform the files backend. Keep in mind that the graphs are log-log. So even though the gap is comparatively small, we are looking at a 3x improvement once we get to writing thousands of references. Finally, one of the most significant use cases why we wanted to have a new backend was deleting references. The x-axis is the number of pre-existing references, whereas the y-axis measures how long it takes to delete a single of those references. And here the reftable backend really leaves the files backend behind in the dust. While the files backend has superlinear growth, deleting references in the reftable backend is constant time. So what's next? The reftable backend is still a rather new addition to Git, so there's still lots of things to do. The first thing to do is that we want to continue improving performance. The files backend has received 19 years of performance optimizations, and the reftable backend has only landed this year. We want to also help other Git implementations, like for example libgit2, to land a backend for it. And maybe we will also eventually end up switching the default format from files backend to the reftable backend. You know, maybe in another 10 years or something like that. In any case, give it a try if you're curious, and let us know how it performs for you. I'm eager to hear your feedback and any kind of insights you might uncover. Thank you.